Hello again and welcome. Today we're going to be looking at this KLEIN Tools MM400. Let's just go ahead and we'll open this thing up. I bought this meter probably a year ago or so, maybe a little longer. Not a very expensive meter. I think this cost under $50. You can see it's rated for 600 volts AC/DC. It's got a 10 amp current shunt. You can read resistance up to 40 mega ohms. Has a DC millivolt range, AC/DC milliamps, microamps. You can see that they mark this as Cat 3 600 volts. It does come with a manual, a couple of probes, and a thermocouple. And of course 2 AAA batteries. I assume it doesn't have any in it. Wow, that switch is tight. You can see it's a single screw holding on the battery cover. It does have a metal insert. Let's just install a couple of AAAs. We'll see if it turns on. Looks like it does, no problem. Boy, that switch is just crazy tight. Let me just go ahead and we'll put the cover back on, and then we'll try running a simple functional test with this thing. And again, for this, we'll just be using our little test box here. I can tell you one problem with this meter right now. You can see the milliamp and the microamp are shared with this common input. So if we transient test this meter, if that fuse is in series with all the functions, it's going to disable this meter as soon as that pops. So I'm not sure yet. We'll have to just take this thing apart. Alright, so let's just see here with DC volts how this thing behaves. So it's on AC right now. This should read 2.5. You can see it's reading 2.47. Again, this should be 2.5 as well, and this should be 2.5. This is at 30 hertz, 15 hertz. Let's just see if we can read frequency with it. I guess we have to go to hertz to do that. So again, this should be 30 hertz. Yeah, it looks like it needs the zero crossing, so you would have to AC couple this input. Let's just see if that works. So this should be 60 hertz. And you can see that's spot on. Let's just see if the duty cycle comes up at 50%. Looks like it does. Again, we'll go back to voltage, and let's just try this with a little higher voltage. This should be 70 volts roughly, AC. So let's just check it with our Bryman. You can see it's 63.8 volts or so. And if we look at the frequency, you can see it's about 3 kilohertz. And so I believe that's why this meter is reading low, is it just doesn't have the bandwidth needed to look at that signal. Let's just select DC. This should be roughly 60 volts. You can see it reads about 56.2. Let's just try it with our 5 volt reference. You can see it's 4.98 or so. That seems to be a little bit low. I'm surprised how slow the auto range is on this. Let's just try this in resistance real quick. Looks like it's in continuity mode. Not sure what that's about. If I touch the leads, it's almost like it double beeps. See that? Every time. I don't know what that's all about. That's a very strange behavior. Alright, so let's go to resistance. And let's see the auto ranging speed on this. So here's an open, here's a short. Wow, it is slow. Here's an open. You can see it's still hunting. And here it is again with a short. Alright, so this is a 1 ohm, 1% resistor. Wow. 1.1. Of course, I have not zeroed this thing out. It does not appear to have a rel. Even if it did, it's reading 0 ohms. Let's try it with our 50 ohm, 0.01%. This is a 100 ohm, 0.01%. This is a 1K, 0.1%. This is a 10K 1%. This is a 100K 0.1%. This is a 1 meg 1%. This is a 10 meg 0.1%. Says it can read up to 40. This is a 40 meg 2%. Looks good. Try it at 100, it should overrange. Let's just try it in capacitance mode. So this is a 150 picofarads. Looks pretty good, about 130. This is a 1 nanofarad. And this is a 0.1 microfarad. Looks pretty good. This is a 1 microfarad. Dead on. Here's a 10 mic. Pretty good. And this is a 100 mic. Wow, it is slow. Here it is with an open. And here's the 10 mic. Whew. Yeah. Definitely not very fast. We could try this in the temperature range real quick. And let's just select Celsius. Again, this should be roughly about 500 degrees Celsius. And this should be roughly 24 degrees. And this should be about 1040. Oh, it overranges. So let's see where it overranges at. Looks like about 543 is where it overranges at. It's pretty low. We can try the microamp setting real quick. This should be 100 microamps. Looks good. Here's 10 microamps and 1 microamp. This would be 100 nanoamps or 0.1 microamps. Looks fine. We can try it in the milliamp setting. I don't like that every time you throw the switch it reverts back to AC, but this meter is really made for electricians. I doubt they're doing a whole lot with the DC modes. Let's just try it here in DC. So this should be 100 microamps again. Wow. See how that thing just kind of creeps up? Yeah, I don't know what's going on with that. Okay, well, it looks like the meter is functional. What I'd like to do now is just go ahead and take this thing apart, and let's see how that fuse is tied into it. Case is a little tight. That's what it looks like on the inside. This is actually pretty thick plastic. So here's our voltage input. You can see that's going off to this resistor network, and it looks like it's also going to this network here. It looks like this is one of our high-speed clamps, and it looks like they have another one up here. This looks like a small gas discharge tube. Alright, let's just see if we ohm this out here real quick. So we've got our input here, and is that going up, I'm assuming, directly to this resistor here? Looks like it is. And is it also going down to this resistor here? Yep, it is. Then it's probably going down to the fuse here as well. Yep. So it looks like the fuse is just for the microamp mode. So what I could do is just pop this fuse out, or we could leave it in there. I guess it doesn't really matter, but it does look like we could test it this way. I am kind of curious. Again, this does look like a small gas discharge tube. Yeah, 90K. Yep, I believe that's what that is. Same thing here, probably 90 as well. Yep. I'm actually quite surprised that this doesn't use chip on board technology. I'm also a little surprised how they're doing the battery holder. You can see they have the springs actually mounted directly to the board. Normally those would be mounted in the case like these two contacts, and then there would be a separate set of little fingers that would reach down to the circuit board to make contact with it. Let's just have a look at these fuses. So this is marked ASTM HV510, 500 milliamps, 600 volts AC. You'll notice it does not have a DC rating. Again, I'm not sure. It may be sand filled. Let's look at a real safety fuse. This one's made by Little Fuse. It's an FLU, 11 amps. You can see it's rated for 1000 volts AC or DC. And it has all the proper certifications on it. So this is a real safety fuse. Compare that again with the fuse that came with this meter. Let's have a look at the higher current fuse. Again, ASTM HV610, 10 amps, 600 volts, AC, DC. So this one I believe is actually rated for what the meter is specified to, but this other one I'm not so sure. You don't see the DC marking on it. Let's go ahead and we'll pop the circuit board out of this real quick. First thing we'll notice is that they are using grease on the circuit board. The second thing we notice is that they've actually got vias inside of the pads here. See that? So one of the problems with this type of a meter is, of course, if I life cycle this, the little divots here are going to ride down inside of those via holes, and that's going to erode the circuit board in those areas. Here's our membrane switch. You can see these are typically what we see with the cheap meters. You can see it uses a couple of springs with some ball bearings. There is a PTC on the bottom side of this board. My guess is that is going right up to this gas discharge tube here. Let's have a look. Does that go right here? It sure does. We can also see it's marked on the circuit board right here. So the input goes to this PTC, right to the gas discharge tube, and then it goes into the switch, and then probably into the drive circuit for the resistance and the capacitance modes. So one of these two high-speed clamps is probably protecting that circuit. We can test that real quick by just reassembling the meter, and then we can take a couple of additional measurements. Okay, you can see I've gone ahead and reinstalled the circuit board. Let's just switch this to the resistance mode. Let's just see if we go from this gas discharge tube up to these clamps here. Yep. And then I assume that the bottom side of these clamps here, that goes back to ground, and it does. So when the meter is in the resistance mode, that is our high-speed clamp. And again, if I just turn the meter off, this is probably no longer connected, and you can see it's not. So that is definitely the clamp for resistance. Let's just try it in capacitance mode real quick, and we'll see if that's using the same clamp. I wouldn't be surprised. So here again to here. Yep. So my guess is if we transient test this, if the meter is repairable, it's probably going to be these two transistors here that get damaged. Alright, let's go ahead and button this thing back up, and we'll try doing some tests with it. Okay, the first thing we're going to do is apply our rectified AC signal. And you can see it's outputting 277 or so bias. You can see it's a reading 118, and again that's because we're looking at the AC mode. If we go to DC, there's 232 volts or so. That's correct. So let's just try this in frequency mode, and in conductivity mode, and then in capacitance mode. And what I'm going to do is just turn this off for a bit so we don't risk popping the fuse. We'll go back to the temperature mode and we'll turn this back on. I can tell you this meter is going to be a pain in the ass to test because you have to go through the current modes to get down to the temperature mode. Alright, let me go ahead and functional test this real quick. So the KLEIN MM400 survived that test just fine. Next I have our little grill starter out. Again, we're going to use this to simulate a ESD event. We'll be applying 5 transients, both positive and negative, with a meter set to each mode. And let's see if we cause any damage. And again, we just flip the leads to reverse the transient. That's it. Let's just go to resistance mode real quick. You can see it's reading an open. That's usually a good sign that there's no problem with the meter. Let's just try measuring our 40 meg resistor. See if there's any problem with leakage. I don't like the fact that it doesn't default to resistance mode. There you go, so 40 meg. So chances are pretty good the meter was not damaged. Let's just try it in capacitance mode. Again, this will be our 150 picofarads. No issue there. I'm not sure what's going on with the voltage mode where it's resetting the meter. If I short the leads out, probably read 0. Yep. I'll go ahead and run through the remainder of the tests. Next, we're going to be using our transient generator to apply a 1000 volt peak with a 100 microsecond full width half height. Again, this transient generator has a 2 ohm source impedance. It's limited to about 20 joules, and again, if the meter doesn't break down, all that energy is dissipated inside of the transient generator itself. This is not connecting these meters directly to a capacitor bank, as some people believe. That's not at all what's going on here. This generator puts out a exponential decaying pulse, just like what a IEC surge generator does. The big difference again between this and the IEC generator is, first of all, this is a 100 microsecond full width half height instead of a 50 microsecond full width half height. And the other big difference is that this is not a combo generator. So while it is based on the voltage waveform, it doesn't meet the profile for the current waveform. It's not even close. So again, the goal here is not to test these meters for safety. What I am looking at is how robust electrically these meters are. Alright, again, we'll be applying 5 transients, positive and negative, with the meter set to each mode. I will say I'm impressed with how they're constructing these meters now. The fact that this has a PTC and a gas discharge tube in it like that, I'm pretty impressed for a $50 meter. Again, we had that Fluke 101 that was also $50, and I never have damaged that meter. If you look at the input protection on that meter, it's built like any other Fluke meter. They did a really good job with that. And again, we have to invert the leads to do the negative transient. Alright, that's it. I'll go ahead and functional test the meter. Let's just quickly go to resistance mode. That just sucks. Alright, what do we get? An open? Yeah, so it looks like the meter's probably going to be okay, but I'll go ahead and check it. Alright, I've checked our meter. Looks like the KLEIN Tools MM400 survived that 1000 volt transient just fine. Transient generator is now set up for a 1.5 kilovolt peak. Again, this is a 100 microsecond full width half height with a 2 ohm source impedance. Okay, that's it. Alright, so the KLEIN Tools MM400 survived that 1.5 kV transient with no issues. I've changed our generator for a 2000 volt peak transient, again 100 microsecond full width half height with a 2 ohm source impedance. Okay, that's it. Let's just check resistance again real quick. Oh, oh, wow, that has damaged the meter. Unbelievable. Let's see what it does in capacitance. So of course, here's with a open, but I mean here's our 0.1 mic. It's not reading capacitance at all. Let's just go to diode check. You can see it's reading a dead short, and of course in resistance it's reading a dead short. Let's just try it in volts real quick. Again, this should read 2.5 volts here and 2.5, so at least that's working. Let's try it in DC. Yep, 5 volts, that's right. Let's try it in our temperature mode real quick. Again, because that is a clamped input. Again, this should be roughly 500 degrees Celsius. Oh, so the temperature is not working. My guess is those couple of diodes fried that I had pointed out. My guess is it's probably these two right here. I think what I'm going to do is just go ahead and pull those out real quick. Let me grab the soldering iron. Okay, we only have to really pull one of these out of here. It doesn't really matter which one. Let's just try this guy right here. Might as well take them both while we're at it though. Only takes a second. Again, it's just these two right here. Let's just check it real quick. We'll just slide our batteries back in. Let's go to resistance mode. Oh, and sure enough, you can see it's reading an open. And let's try it in capacitance mode. Yep. See, it's reading 0.01 nanofarad. And in temperature, and my guess is the meter is probably working now. Let's just verify that real quick. So if we go to Celsius, again, this should be roughly 500 degrees C. You can see 495, and here we are at room temp. And again, the meter can't read up to 1,000, but it looks okay. And let's try it in capacitance mode. This will be our 1 nanofarad capacitor. And you can see that's reading correct, and this is our 0.1. That's correct. Let's just try it in resistance mode. Again, there's continuity. That's correct now. And let's just try it with our 40 mega ohm. Yep. So these diodes here are probably leaking. Yep. It's dead shorted. Let me just see what these parts are. Again, those two transistors that have failed, they're marked 6BW. I believe that's a BC846BW or it's a BC817. So these are a high frequency small signal transistor. You could probably replace these with any jelly bean part. That's basically what I've done, is I've replaced these with a little more beefy transistor. I've used these before on other meters for repairs where I've tried to enhance their robustness. So I have no doubt that these are going to work fine in this particular meter. So here's our two new parts. And does it read and open? It looks like it does. So we'll go ahead and check this thing out. But yeah, I believe that we're in good shape. That's one of the good things about some of these cheaper meters, is that we're actually able to repair them, and that keeps things out of the landfill. So in my opinion, it's always better to get a more robust meter, because stuff does happen here on the bench. Again, I'm not an electrician, so I really don't care about the safety aspects of these meters, but I do expose them to transients every now and then on the bench, not necessarily on purpose, but stuff does happen. Alright, let's have a look here. So again, we'll try conductance mode, and that seems to function fine. Let's go to resistance. Again, this will be our 50 ohm. Here's our 100 ohm. Here's our 1K ohm, 10K ohm, 100K ohm, 1 meg, 10 meg, and this will be our 40 meg. Looks good. Let's just try the capacitance. Again, this will be our 1 nanofarad, and here's our 0.1 microfarads, and here's our 1 mic, and here's our 10 mic. Slow auto range. Here's our 100 mic, and let's just try it in diode check, which we didn't look at before. So here's an open, here's a dead short. Let's just try it with a single silicon diode. Here's two in series. Let's just try our little white LED. You can see it lights that just fine, and we're getting about 2.6 volts. We can just check the open circuit voltage real quick with this using our other Bryman. Let's see what we get. So about 3.2 volts for the test voltage. Plenty high for most applications. Let's again go to temperature. Again, this should be roughly room temperature, or about 24 degrees Celsius. That is fine. And with our pot set somewhere in the center, this should give us roughly 500 degrees Celsius. And you can see it's about 510. Again, this is kind of a touchy adjustment here, but looks okay. So no worse for the wear, but not a very robust meter. Again, even with these bigger transistors in here, when I had this apart, you could see it used the smaller body size PTC. If I increase the level of the transient, I think what would happen is that small body PTC is eventually going to break down, and the GDT isn't going to be very fast, so that transient is probably going to blow through right into those two transistors. Would those survive long enough to actually save the meter? Hard to say. Typically what happens is the energy increases will actually blow those two transistors open. That transient then passes down into the main IC, and that's when we damage the main controller, and basically we can no longer repair the meters at that point. Well, I think that's going to be it for this video. Hopefully you've enjoyed looking at this KLEIN MM400. Again, this meter costs less than $50. And it was repairable, so I have to give it kudos for that. If you want a smaller meter for electrical work, maybe this would be a good choice for you. As far as doing electronics type work, I really wouldn't have a use for this type of a meter. I would want something more like this BM869S, where we have multiple displays. We can measure AC plus DC. Of course, with this meter, it has 2 thermocouple inputs. So there's a lot of advantages to having a meter like this if you're working with electronics. Not so much with something like this. Well, that's going to be it for now. We'll see you in the next video. Later.